Example of, wow, so when I pick it up, if I do this, if it's doing that much, that would be a large earthquake. All right, so now I put my 3 points in randomly, and what I'm going to do is just draw in a triangle for this. So when I draw in a triangle, just connect the points, and go ahead and connect all three. And when you're drawing the triangle in, what you're really doing is drawing in a you're drawing in the triangulation that you do for this. Now, if I have intensity at A, B, and C that's the same, then that means there's some point on this map that it takes the exact same amount of time from this point, this center point, to get to A, to get to B, and to get to C. Does that make sense? That it has to be the same. For the intensity to be the same, the distance traveled need to be the same. That I'm finding out where I'm dropping the rock into the pond. So in essence, what's happening here is these are 3 measurement sites. They all have their iPads sitting on a desk, and it measures the same intensity in all 3 of these cities. They would use a real seismometer, not an iPad. But we should be able to find the epicenter from this. Now, the way we're going to do that is we know if it's the same from A and B, then it must lie on a line that's the same distance from A and B, right? Does that make sense? So in other words, if I'm finding a point that is the same from A to B, all the points that are the exact same distance from A to B lie on a perpendicular bisector. They have to. Because if I said, like this point down here, is this the same distance from A to B? It isn't. How about this point over here? No. But what if I put something like that? It would make an isosceles triangle, right? And that isosceles triangle, if I dropped a perpendicular through that isosceles triangle, it'd go right through the middle of the base. And that's what I'm actually trying to look for. So any point along a perpendicular bisector, if I pick that point, it has to be the exact same from A as it is to B. Now I want you to think about this. If I draw a perpendicular line through A and B, because it's the same distance from A and B, and I do the exact same thing to B and C, those 2 lines are going to cross somewhere, right? Because we know they're not parallel. The 3 points of the triangle that are randomly put in there, if they're not in a line, if they're non-collinear, then a perpendicular bisector of one is automatically going to cross a perpendicular bisector of the other one. Does that make sense? That 1 point where they cross is going to be the same from A to B as it is from A to C as it is from B to C. It has to be, all right? So you can get away with just doing 2 of these, but I'm going to show you on this. We're going to use that method, and there's going to be a lot of lines in here, so I'm going to try and draw them gently. So I'm going to use the perpendicular bisector method on A to B here. That's what I'm doing with this one. So I use that same rhombus method, and I'm just going to kind of gently draw up here where they cross, because that's what's going to give me my rhombus. So the crossing point here and here is going to be the perpendicular bisector, the opposite diagonal of the line segment AB. Does everybody kind of see that? Now I'm going to draw this in fairly heavy. So there's my perpendicular bisector between A and B. Would you agree that every single point on this line has to be the same distance from A as it is to the B? Does it look like it? Kind of makes sense? Now go ahead, if you will, on yours, the one that you just practiced on, and you can do this a number of different ways, but you drew in this perpendicular bisector, right? What I'd like you to do, just for the sake of the kids and what you will do for them, is pick a random point on that line and then measure the distance from A to that point and from B to that point, and you should get the same value. So go ahead.